Okay. Yes, everything is ready. Hi everyone. By the way, I posted the first assignment today, and please do the assignment. And as you know, it will not be graded, so there is no submission for that. But I have given you about 2 weeks, so you practice it and do the assignment. Then I will upload the solution. And please do that because exam will be more or less, not exactly, but more or less similar to the assignments questions. So you will understand the taste of questions. And as you will see, there is no proof there, just solving the different algorithms. So you'll have toy data sets, for example, and you apply the algorithms on them. Also, your midterm exam, I will announce its time soon. I need to make sure about the date of reading week. I'm not sure. Do we have reading week this semester? And is it a full week? Okay, let me double check the calendar. So next week is the. Do you mean that next Thursday we don't have a class? We do. Okay, the next 2 weeks you mean? Okay. So usually the semesters, as far as I know, the semesters have the fall and winter semesters have one reading week, but the summer semester usually doesn't have a reading week. But this semester, I was in doubt because once we checked and I checked and saw that there was no full reading week in the calendar, but I might be mistaken. So I will go and double check that. So, but I can accept your word. So you're saying that next 2 weeks is reading week, right? The whole week. Does it mean that deep learning also? Yes, please, thank you. Then we can decide about the midterm exam. Of course, the midterm exam will be after the deadline of the first assignment, because you need some time, at least several days, to check the solution key that I will upload, right? Okay. So that's one thing. Any question before we continue? No? Okay. So last session we talked about LDA. I believe we came up to here. So we said that LDA assumes that the covariance matrices are equal to each other, and then we do remember in LDA and QDA we said that the posteriors are equal to each other. Do you remember? And we know that posterior is likelihood times prior, right? Over the other prior, but the other priors are constant, so equal for both sides. They are cancelled with each other. Therefore, we'll have a likelihood times prior equal that likelihood times prior for the other one, right? Now we put the so sigma 1 equals sigma 2 equals sigma, and we put them in the equations, right? Then what happens? We'll have these, and I think you understand why we have made this assumption in LDA, because we want to simplify the equation, right? So what happens if we do that? These two, October to 11, so the whole week. Thank you. October 6 to October 11, but it's not a whole week. How is it? Friday to Wednesday. So basically that's exactly what I was saying. There is no so we will have all Thursdays class, right? So October 5 we have class. October 12 is after the reading. It's weird, I agree. Usually reading weeks start from Monday until Friday. Yeah, I still don't know. Okay, so October 6th until October 11 is a reading week. So basically it means that at least for statistical machine learning, all weeks we have class. Okay. And I need to count how many sessions we have until the end. Also, I'm not sure. Is it 10 or 11 sessions? It must be 10, I guess. Usually they set the calendar in a way that we have 10 sessions per semester. But we need to count. Okay. Thank you very much for listening. So we said that, okay, these are equal to each other, and these terms get simplified. Why? Because we have assumed that the covariance matrices are equal to each other in the LDA, right? Then we'll have this. Then what happens? Then these, I have exponential operators. So usually they're a pain in the neck. So we'll use the opposite operator, which is natural logarithm, right? So take natural logarithm from the sides. Then what happens? We'll have this. We know that log of a b equals log of a plus log of b. Therefore, plus log of pi 1. Likewise, here we have them. Okay. Then, sorry, where were we? Okay, we were here. Then we said, let's simplify this. We worked it out. I'm not going to repeat that again. And we ended up in equation 19. So we replaced equation 19 in the equation that we had. And we have these. Then we rearranged the terms. So brought everything in one side of the equation, right? Then we factor out, for example, x. And we ended up with equation 20. And what did we say? We said this equation 20 is a linear equation with respect to x, right? Where this is in the form of A transpose x plus b equals 0, and where x is a vector and A is also a vector, b is a scalar, right? B here, and this is exactly an affine equation, right? This is an equation of a you can say hyperplane. So here, A, you can see it as either a slope or as it is multidimensional or normal vector on the hyperplane, right? And B is the intercept. So where it cuts one of the axes. So, and we said, hence the name linear discriminant analysis, because its decision boundary is linear, right? Okay, so for obtaining that equation 20, we brought the expressions to the right side, which was corresponding to the second class, right? One of the. Therefore, if we use what we had, this is exactly this part that is exactly equation 20, which was set to 0, right? Now this time I'm saying that consider this, I define it to be a function rather than equating that to 0, okay? So I denote that function by delta x, and this function gets at rd x, d-dimensional x, and outputs a scalar, right? So this is actually the decision boundary, which is a linear function. And we know that if delta x is less than 0, it's in class 1. If delta x is greater than 0, it's class 2y. Because delta x is the equation of that hyperplane or line. If delta x is less than 0, it means that I'm below the hyperplane. If delta x is greater than 0, I'm above the hyperplane. So it's one of the classes, right? Because this hyperplane is separating the two classes. Now, we said that if we can also simplify this equation further, if the priors of the two classes are equal, if pi 1 equals pi 2, then this term goes away, right? Because pi 2 over pi 1 will be 1, and logarithm of 1 is 0. So we'll have this. But by the way, I will talk about it, but let me tell you in advance, how do we calculate pi 1 and pi 2? Can you give me suggestions? By the way, be brave in giving suggestions. In the worst case, you are wrong. That's fine. Be brave. Give suggestions. How do we calculate pi 1 and pi 2? No. So I don't mean from here, because I need to have pi1 and pi2 to put in this equation. I'm saying that how do you, without this equation, how do you calculate pi? What was pi1? It was prior of the class 1. So I have to assume in my data set I have several classes. How can I calculate the prior of a class? Okay, that's a good answer, right? Exactly what you said. So let's count the population of this class. Also, we have the total population, right? Divide this population of class over the whole population. It will be a number between 0 and 1. You can assume that it is a prior probability of that class, right? So we can estimate. Of course, this is estimation. Estimate the prior of the class in this way. As a result, if so what is this term doing in LDA? It's basically taking into account that what if my classes are imbalanced, right? Then it affects the decision boundary, right? I think it makes sense, right? Why? Let me give you this example. Consider a very busy class, too many points, and very small class. So I think a rational decision is that we move the decision boundary closer to this one. If it was bigger, then we would move the decision boundary here, right? This is exactly what LDA is kind of doing. It's tuning the as an intercept. It's tuning the decision boundary based on the population of classes. We will discuss it further in a few slides. Now, quadratic discriminant analysis. So basically, if we surpass our assumption, saying that if we relax that assumption that who says that the covariance matrices are equal in the two classes? In general, they might not be equal, right? So if they are not equal, then we have sigma 1 and sigma 2 rather than sigma. Then in this equation that we had, I can't cancel these two terms anymore. Agreed? But they are pains in the neck. What do we do? This, of course, we have also exponential operator. So it recommends that we take natural logarithm from the size. Let's do that. So we'll have logarithm of this term becomes, so logarithm of a over b is minus logarithm of a, right? Also, I have all of these. So we know that logarithm of a to the power of b is b logarithm of a, and b here is what? You tell me. Power minus half, right? Minus half. Half is because of the square root, minus because it's in the denominator. And also I have some elements here. So in general, for this term, I will have minus d over 2, natural logarithm of 2 pi. Also, I have minus half logarithm of determinant of sigma 1. And the rest is as before. Likewise for the right-hand side. Note that here we have sigma 1 and also sigma 2, right? Now we need to simplify it. Of course, its simplification is harder, right, than LDA. So, sorry, yes, here. Do you remember equation 19? We simplified this in previous session, and I just briefly talked about it a few minutes ago. Do you remember this simplification that we made in the previous session at the end of the previous session? Okay, so I'm gonna use the same simplification here, but this time rather than sigma, I have either sigma 1 or sigma 2, right? So these will be sigma 1 or sigma 2. Understood? Okay, so as I have said here, recall equation 19, the simplification in equation 19. And as a result, let's replace these terms in the previous equation. So basically, I will end up with this equation. Now, let's multiply the sides of this equation by 2. Why? Because I have a lot of halves, 1 over 2. So if I do that, this term, these halves will go away, but these 2 will be multiplied by 2. And also I bring all of them to one side. And then I factor out here x, right? I right factor out x. So I will have these from these two equations, I mean, right factor out x. I will have these. Likewise, from these two, what can we do? I can left factor out x transpose and right factor out x. Agree? To get this. What about these two? These two, I have written them here. And what about these two? I have written them here. No, sorry, apologize. These two, I have written them here. What about these two? I have written them here. Agreed? Just simple calculus, right? And now, what is this? What is this equation in terms of x? It's a quadratic equation with respect to x in this form. X transpose ax plus b transpose x plus c. In other words, if it was a scalar, it would be like x squared plus ax squared plus bx plus c equals 0. But now this is vector. Therefore, I'll have x transpose ax plus b transpose x plus c equals 0. Right? Now, hence the name quadratic discriminant analysis. Because its decision boundary is quadratic, right? When I say quadratic, think of a bowl. A bowl in 2D is like this. A bowl in 3D is like what? Imagine the skin of egg. The skin of egg, right? Consider a skin of egg, which is going up forever. So now I want you to imagine, assume I want to apply, we have two classes in this class, for example. One class, you 4 points, you 4 people in one class, you other in the other class. So we have two classes in the two sides of the class. Of course, you are separable, linearly separable, also quadratically separable. So LDA can and QDA can separate you guys. If I apply LDA in this, so and the space is 3D, right? If I apply an LDA, what will be the decision boundary? It will be a wall between you. A wall. Separating the class into two parts, right? A wall, yeah, a wall, sir. A plane, a wall, right? What about if we apply QDA? It will be like a curvy wall, which is like an egg. So it's not just curved in this direction, also in this direction. So curved in both directions. Did you understand? Okay. And I think if we apply here, for people who are watching, they don't know. Here in this side, we have more people, right? And less people here. Therefore, the curve would be where, in which direction? It will be like this. Obviously, right? So the curved direction also is decided by the population usually. So now, as before, let's define this equation, which was equal to 0, as a delta x, and this will be the decision function, right? If delta x is less than 0, it means that we are below the quadratic function, which is class 1. Otherwise, it's class 2. And I think, yes, you can find out that I have pi 2 in the numerator. That's the reason if I'm above that, it's class 2. If you bring all of them to the other side, then we'll have logarithm of pi 1 over pi 2. Then this equation will be the other way around, right? Okay, doesn't matter. So again, if the priors of the classes are equal to each other, it becomes simplified to this. The last term will go away, right? Now you tell me, what happens if the covariances of the classes are actually equal to each other? If you calculate the covariances of the two classes and you see that they are actually equal, it means that sigma 1 and sigma 2 are equal to each other. Let's put sigma 1 equals sigma 2 in this equation. What happens? So the first term, which is quadratic, goes away, becomes 0, and the rest, this also gets simplified, right? Because you will have sigma inverse, so you can left factor out sigma inverse. Note that we have still mu2 and mu1, right? So it doesn't become 0. As a result, this becomes a linear equation. So QDA reduces to LDA. I think it's obvious because LDA exactly made this assumption of sigma 1 equals sigma 2, right? So far we talked about LDA and QDA for binary classes. What if we have multi-class classification, right? Also note that whenever you have multi-class classification, you can always break it down into several binary classification, right? Assume you have 3 classes, then you can consider it as 3 binary classification problems, because you can say classification of class 1 and 2, classification of class 1 and 3, classification of class 2 and 3, right? So, but here we say now consider multiple classes which can be more than 2, indexed by k. K goes from 1 to c, the number of classes, right? Recall equation 12 or 15, where we were using the scaled posterior. This was the scaled posterior, right? Likelihood times the prior. So let's see what happens. This is the likelihood that we assumed is Gaussian, right? And this is the prior. But note that now I'm using k as the index of the class. So let's take natural logarithm from this equation. Of course, becomes logarithm of fx pi k becomes this. Take logarithm from this right-hand side. It simplifies to this, right? By calculus, simple calculus. I dropped this part. Why? Because it's the same for all classes. This is for kth class, right? And I know that this term is constant. It's not related to k. Therefore, I can drop it because it's equal for all of the classes. Let's get rid of that. And we know that this term is multiplied before taking the logarithm. This term actually, right? Thus, the scaled posterior of the kth class becomes this. So this is this equation 28 is exactly this equation dropping this first term, right? I can consider this function as a decision function for which class the point belongs to. So whatever class which maximizes this delta determines the estimated class for that, right? So what do I mean? I have delta 1 to delta c, right? I have c, assume c the number of classes. I have delta 1 to delta c equations, right? Now an x comes. It can be a test point, training point, whatever. Some x in the space. I feed this x to all of the c equations. It gives me delta 1 of x, delta 2 of x, until delta c of x, right? Then one of them is maximum. That determines which class it belongs to. In LDA, we assume that sigma 1 until sigma c are equal to each other, right? In LDA, we assume that all of the covariance matrices are equal, and now we have C classes. So let's put that assumption in the decision function, see what happens. If we do that, so this was what we had in equation 28. If we do that, delta k becomes delta. Sorry, sigma k becomes sigma. Then, but still I have mu k and pi k. Then what happens? I can multiply the terms of these parentheses to each other, considering the sigma inverse in the middle, right? So I'll have these. Let me think. I have these terms. I had 4 terms, but 2 of the terms were equal to each other, so I summed them. So I had plus half mu transpose sigma inverse x plus half mu transpose sigma inverse x, so it became 1 mu transpose sigma inverse x, right? Agreed? Interrupt me wherever you didn't follow me. Okay, so as a result, the decision function got simplified for LDA, but we can simplify it further. Let's drop the constant terms again, because they are repeated for all of the deltas, and we know that they are not dependent on K, so they are equal for all of the classes. So let's get rid of this term. Also, interestingly, this term doesn't depend on K. Agree? So it gets more simplified to equation 31. And this is the decision function for multi-class classification in LDA. Agreed? And whichever class maximizes that determines the class of that point. But for QDA, we should use equation 28, right? For QDA doesn't make the assumption of equal covariances. Now, estimation of parameters in LDA and QDA. How do we calculate pi, sigma, and mu, right? So as I said, we talked about this. The priors of the classes can be estimated as the cardinality of that class over the population, the total sample size, right? The total number of points. So nk is the population of class and n is the total number of points. We can do that. This is just an estimation. Of course, the more accurate your estimation, the better the performance of LDA and QDA, right? Now you tell me, how can I estimate mu and sigma? I have said it here, but if you don't look at this, how can I estimate mu and sigma? The mean and covariance. So here I assume that the distribution of the class is Gaussian, right? You tell me. So I have a Gaussian distribution. It has some mean and covariance. How do I calculate the mean and covariance of the Gaussian distribution? You remember? What was the mean formula for mean of the Gaussian? Mean of the distribution means expectation of that distribution. What is the expectation of Gaussian? If you don't know, don't worry, you can look it up, but it's exactly average. So for some distributions, including Gaussian distribution, the mean is the average. Okay, not for all distributions. And I think now you understand in between public, whenever we say mean, public people think that we are talking about average, right? Because in their mind, they're assuming that the distribution is Gaussian. This assumption is kind of valid because the most common distribution for continuous random variables is Gaussian, right? This is their assumption behind their minds. So we can use mean. And what is it? This is exactly the average, the average of the points in the class. Why? What is this? This is indicator function, which is 1 if its condition is satisfied, otherwise 0. So I'm basically saying that it says this indicator function says whether a point is in this class or not. If it is not in the class, it becomes 0 and it is not contributed in the summation. So basically it means that you just sum over the points in the class, how many points I have. So only sum xi's in the class and then divide them by the number of points in the class. So it's basically the mean of the class, the average of the class, right? By the way, I don't know if you have heard of this or not. We'll talk about it in a few lectures, but maximum likelihood estimation, if we don't know, we will cover it. But maximum likelihood estimation, just one of the techniques to find the parameters of the distribution, right? Another one, we have several techniques, such as maximum a posteriori. There was another one too, which had moments in it. So there were at least 3 techniques: maximum likelihood estimation, maximum a posteriori, and something which had moment in it. Sorry, I forgot its name. But the most common ones are these 2: maximum likelihood estimation, or MLE in short. The other one, maximum a posteriori, or in short, map. Okay. By the name, I think it's obvious. What does it mean? When I say maximum likelihood estimation, I assume I'm saying that maximize this likelihood with respect to the parameter. And that parameter once can be mean, once can be covariance, but this is the parameters of the distribution. Every distribution has some parameters, right? For example, Poisson distribution, I don't know if you have heard of that. This is some distribution. Its parameter is lambda. Gaussian distribution is parameters. It has two parameters, mean and covariance, right? So we can find these parameters. How? We say which value of this parameter maximizes my likelihood. I think it makes sense, right? This is maximum likelihood estimation. Maximum a posteriori says that which value for the parameters maximizes the posterior rather than the likelihood, right? And posterior is the likelihood times the prior, right? So whenever prior is important to you, you should use maximum a posteriori, because in maximum likelihood estimation, you ignore the prior. Now I think you understand that when your data is imbalanced, prior is important. So you should use maximum a posteriori. By the way, there's another thing which we'll cover in this course, and that's expectation maximization. We'll see that soon. What does it do? Its name might be scary, but its concept is very easy. It's very easy. It says that basically it's when you want to do maximum likelihood estimation, if you can, do it. But sometimes a part of your data is not completely obvious. So you have some missing information in your data. When this happens, you can't apply maximum likelihood estimation directly. Then you replace that missing data with the mean of data. You need to kind of compensate that missing data. What is the best compensation? Replacing with the mean of data. This is, and then do maximum likelihood estimation. Replacing the missing data with the mean of the data and then doing maximum likelihood estimation is called expectation maximization. And I think by its name now became obvious to you. Why do we call it expectation maximization? These are the two steps that we are doing. Expectation, replacing the missing data with expected value, the mean, and then maximization, maximize the likelihood estimation. Likelihood, so do you remember Bayes' rule? Let me add a page. Probability of, just give me a second. Yeah, oh, yes, I think. Probability is X, no, C. I think C given. X, hopefully I'm right. Yes, I'm right. Probability of class given data. Well, when I say class, I mean the label, right? The label given data equals probability of data given label given class times probability of class over probability of data, right? And this is exactly what we use in LGA and QDA. We use this posterior. So when we are using this posterior, according to Bayes' rule, this is equal to whole this, right? But we got rid of the denominator because it was equal for all of the classes. P of X, right? It's not P of class, it's the P of probability of the whole data, disregarding the classes, right? So it's equal to for all of them, so we ignored that. And we were talking about these two in LDA and QDA, right? Some classifiers only work directly on the posterior. We will see that. And that is logistic regression. We'll see that, okay? So logistic regression works directly on that. LDA works on the right-hand side of the Bayes rule, okay? But this is called posterior. This part is called likelihood. This part is called prior of the class. This part is called prior of data. This likelihood is also called class conditional. These priors are also sometimes called marginal data, marginal probabilities. Do you know why? Recall preliminaries. We can marginalize probability to get rid of, for example, I can say P of X equals summation of P of X given C for all C's. This is marginalization. That's why sometimes prior is also called marginal. Yeah, so the likelihood times the prior is, so P of X given C times P of C, you can write it as P of X and C. Am I right? Join this, this one. You're right. Sorry about that. So in other words, you can write it as P of X given C, P of C. Yeah, sorry about that. Yeah, thank you. So did you get the names? And just, I have said it several times, but let me tell you once more, I think it's cool. So and these terminologies have been borrowed by mathematics from philosophy. Posterior in philosophy, we had a posteriori propositions. We also had a priori propositions, and these are Latin words, which means that the things that we understand after experiencing the world or before experiencing the world. For example, when I say 2 + 3 = 5, of course, this is a priori. Do you see 2 in the world? You always see 2 things. Don't see the number 2, the digit 2. You need to imagine it, right? So when I say 2 + 3 = 5, it's a priori experience. It's a proposition. Okay. So let's go back to where we were. I was talking about MLE, map expectation maximization, right? So if you do MLE for Gaussian distribution, it gives you these estimations. The mean becomes this, and the covariance becomes this. This is the MLE estimation for covariance in Gaussian distribution, right? Also, you should note that this is called a biased estimation of MLE. What do I mean by bias? Sigma expectation of sigma k hat is not equal to sigma, right? Recall preliminaries. It is a bias estimation, right? In order to make it unbiased, people put 1 - 1 in the denominator. The reason is that when you calculate this expectation, let me tell you, expectation of this sigma hat becomes, if you can find its proof in Wikipedia, it's a straightforward, but I think, let me remember, it becomes, yes, if you apply expectation on equation 34, it becomes this: nk - 1 over nk times sigma. Sigma is the actual thing, right? Which we want to estimate. As you see, it's not equal to sigma, because nk - 1 over nk is not 1. What can we do to make it unbiased estimation? So expectation of sigma hat becomes exactly sigma. Simply replace nk in the denominator by nk - 1. Then it becomes nk - 1 over nk - 1, which is 1. Did you understand? Nothing complicated. So that's why it's called unbiased estimation of the covariance matrix. By the way, the statisticians call these two sample covariance matrix, because we use sample twice. It's a quadratic thing, right? They also call this sample mean, because we use sample, the average of sample, as estimation of mean. Now you tell me, what should I do for calculating the sigma in LDA? Because in LDA, I was assuming that the covariance matrices of the classes are equal. Now I calculated the covariance matrices of my classes, and they are different. But I want to use LDA still. What should I do? I need to have a shared sigma, right? So I can assume my shared sigma is the average of, weighted average of the covariance matrices of the classes, where the weights are the cardinality of the classes. Did you get it? Okay, some example of LDA and QDA. Please take a look at this. This is very cool. See this? This is, by the way, I coded that several years ago when I was a PhD student. Because I have written a tutorial in LDA and QDA, and I have put them in the paper. So you can see the code in my GitHub page for LDA and QDA. Consider this: the top row is for LDA, the bottom row is for QDA, and here we have, for example, two classes. As you see, LDA, but its boundary is a line, and as you see, it has partitioned the space. Here, my dimensionality is 2, right? So my decision boundary became a line. If it was 3, it would become a plane, right? Now, if I have 3 classes, therefore I have 3 lines, right, between the classes. It's basically, it was like this. They were continued. What we don't consider, we only consider where they intersect each other, right? The lines, the decision boundaries. What if I have one of my classes, or at least one of my classes is multimodal? What do I mean by multimodal? It has several modes. You know what is mode, right? Don't you? So this is one mode. This is 2 modes. Assume this is PDF, probability distribution, density function, probability density function. So when I have like this, I have 2 modes. When I say unimodal, I have 1 mode. If it is multimodal, Gaussian, so LDA might not work very well. Can you tell me why? Can you tell me why? Please give me your suggestions. Why, if I have multimodal classes data, LDA might fail a bit, not perform very well? I assume that in both LDA and QDA, I assume that the distribution of the classes are what? Gaussian distributions, right? And that Gaussian distribution was a unimodal Gaussian distribution. Was it a mixture of Gaussian distributions? No, it was one Gaussian distribution per class. So if my class is multimodal distribution, simply it violates my main assumption in LDA and QDA, right? Also, QDA, as you see, is quadratic. Also, if I have 3 classes, then I have 3 quadratic decision boundaries between them. And this is QDA and the multimodal.
They use the Gaussian distribution as the sample, so they sample data from Gaussian distribution.
Yeah, so Gaussian distribution is the most common distribution for continuous random variables. And it has been empirically seen that in nature, even the cells in our eyes work like Gaussian distribution. So they work like Gabor filter. I don't know if you have heard of this. Just Google it, Gabor filter. If you have passed any course in image processing or computer vision, you might have seen that. So Gabor filters are like, I think this is cool. Let me show you what Gabor filter is. Yes. This is Gabor filter. You see that? What is it? A Gaussian, which is riding, which is on a sine. What do I mean? You know, sine is like this, right? Sorry. You know, sine is like this, right? When you make it, a Gaussian is riding on the sine, it becomes like this, right? Something like that, right? Or so basically, Gabor filters it has several components. It has sine, it has Gaussian exponential operator. Also, it has some angle. So because in 2D, you can have this sine in this way, or in this way, or this way, right? Some angle, right? So actually, our eyes have Gabor filters. And as a result, it works with Gaussian distribution. And even in the world, we have we see a lot of Gaussian distributions. There is another reason that Gaussian distribution is important. Can you guess? Have you heard of what was his name? What was his name? When you add too many values with any distribution, they converge to Gaussian distribution. Central limit theorem. Central limit theorem. This also explains why Gaussian distribution is the most common distribution in the world. It can be proved in a statistics that give me a bunch of random variables. These random variables might be from different distributions, might have any distribution. I sum them up, and I assume that a number of these values, the population goes to infinity. So I limit the population to infinity. If I have too many values summing up, the distribution of the whole thing becomes Gaussian. This is called central limit theorem. That's very cool, right? By the way, in discrete random variables, the most common distribution is Poisson distribution, written in this way. I think it has 1 or 2 S's. I don't remember. Okay. So LD and QD as metric learning are metric learning. Let's see. Recall equation 28. Remember that this was equation 28 that we had for multi-class classification in I think QDA. Okay. First, assume that the covariance matrices are all equal as we have in LDA for now. Okay, and they are all identity matrix. We will relax this assumption, but for now, assume that they are all equal to each other and they are identity matrix. Which means that all classes are assumed to be spherically distributed in the D-dimensional space, right? When the covariance matrix is identity, it was like the distribution of the points is like a sphere, hypersphere, right, in the space. After this assumption, this equation 28 becomes what? Becomes simplified to equation 38. Why? Can you tell me what is? So sigma inverse becomes identity inverse. Identity inverse is identity, right? And also, what is determinant of the identity matrix? It's 1. What is logarithm of 1? 0. So I will have this. Agree? Now, if we assume that the priors are all equal, also assume that the priors are all equal. So I can also get rid of this term because this will be the same for all of them, right? Then it becomes more simplified to this. But what is this? Take a careful look at this. What is this? Minus half x minus mu k transpose x minus mu k. Ignore also minus half for now. What is x minus mu k transpose x minus mu k? See equation 40. What is the L2 norm of x minus mu k? It's this, right? Do you agree? And what is L2 norm of x minus mu k? What is that? When I say L2 norm of a vector minus another vector, what does it mean? The length of the vector connecting these 2 points, right? So basically means that what is the distance? This is the distance, right? Euclidean distance. X minus mu k L2 norm, it means that what is the Euclidean distance between these two? Basically, it means that what is the length of the vector connecting these 2 points together, right? Did you understand? So basically, it is minus half dk to the power of 2, and dk is the Euclidean distance to the power of 2 to get rid of this square root, right? So basically, QDA or LDA reduced to simple Euclidean distance from the means of the classes if the covariance matrices are all identity matrix and priors are equal. In other words, What does equation 39 tell me? It basically means, forget this for now. Assume you want a baby to classify this space for you. A baby who doesn't know any machine learning. You tell the baby that I have the mean of my classes are this and this, these 2 points. This is the mean of class 1. This is the mean of class 2. Now I have a test point here. What class it belongs to? What will the baby tell you without any knowledge of machine learning? What is the in other words, my question is this: what is the simplest classifier where a baby can also figure it out? Distance, exact. Calculate the distance of this point from the means of these two classes. With whatever distance is smaller, means that this point belongs to that class. Agreed? So basically, as we saw, QDA reduced to Euclidean distance. Basically, it means that if I make this assumption of equation 37, and assuming that the priors are equal to each other, basically LDA or QDA are measuring the distance to the means of the classes. The simplest classifier, right? However, now let's relax that assumption. So because this was not an art, a baby could figure it out. But what is LDA and QDA? What are they doing? Let's see. Now consider the case where still the covariance matrices are all identity matrix. I will relax this assumption also. But the priors are not equal. So I'm relaxing the assumption of having equal priors of the classes, right? Then what happens? Then I will still have this term, right? The logarithm of pi k. What is it doing? Let's analyze it. If we take exponential, which is the inverse of logarithm, right? From this expression, this logarithm of pi k becomes pi k, right? And the pi k becomes a scale factor weight. Why? Because I know that logarithm of a plus b becomes logarithm of ab. Agreed? We know that pi k will be kind of multiplied as a scale factor, as a weight. Okay. Just give me a second. Sorry, I'm taking exponential from the sides. So it will be exponential of I got confused a bit. That doesn't matter. So I'm basically, this is kind of a scale factor. But let me analyze what this scale factor is doing. This means that we still are using distance metric to measure the distance of the instance because of the first term from the means of the classes, but we are scaling the distances by the priors of the classes. So that last term is kind of a scaling. And what is this scaling doing? If a class happens more, which means its pi k is larger, right? Then its prior is larger. It must have a larger posterior. So we reduce the distance from the mean of its class. In other words, if pi 1, consider this figure. If pi 1 equals pi 2, and these are the means of the two classes, right? When the priors of the classes are equal to each other, the decision boundary should be exactly between them, right? Because their priors are the same, so everything should be equally divided between them. The space should be equally divided between them. But what if pi 1 is less than pi 2? In other words, the class 2 has more number of points. The class 2 is more powerful, right? So it's more powerful, so it's just more space, right? It says I'm powerful, you can't say anything to me, right? So the decision boundary is pushed away from it. If pi 1 is greater than pi 2, class 1 is powerful and says I'm strong, so it pushes the decision boundary away. And how is this decision boundary pushed? Exactly by this term, right? Now, did you understand what LDA and QDA is doing? It's basically the simple idea of classification, but it scales the decision boundary, right? And what, by the way, here, when I say the decision boundary is exactly between them, still I'm using the idea of that baby, because if a point is this side of the decision boundary, its Euclidean distance is smaller to that, right? What? Decision boundary, we already found its formula, right? This, do you remember? We already, here in these slides, I'm analyzing them. Now, so LDA and QLDA, we derived their formulas, we proved them. Now let's analyze them, what they are doing. Okay. Here I'm telling you that that LDA and QDA are kind of metric learning. What do I mean by metric learning in machine learning? Metric learning means that metric is short for distance metric, right? Actually, we are learning the distance metric. So here, if we don't do any metric learning, we are using Euclidean distance. But we can modify this distance according to our desire. This is called metric learning, right? This is exactly what LDA and QD are doing. They're modifying this distance, right? When I say modify the distance, you can translate this sentence to modify the decision boundary, right? We can calculate pi 1 and pi 2 by dividing the population of class by the total population. Yes, they are scalars. Do you remember? Yeah, we said how to estimate pi 1 and pi 2 in this slide. Right? So now let's relax the other assumption. Now, also consider that assume that covariance matrices are not equal, as we have in QDA, general QDA. Then what happens? Let's analyze this case. Let's apply SVD, singular value decomposition, on the covariance matrix. You can also consider it as eigenvalue decomposition, because if you apply SVD on a square matrix, a square symmetric matrix, its behavior becomes similar to the eigenvalue decomposition. Can you tell me why? Because in SVD we had U sigma V transpose, then it becomes U sigma U transpose because it's square and symmetric. And U sigma U transpose is very similar to what we had in eigenvalue decomposition. So either eigenvalue decomposition or singular value decomposition. On sigma, you will have, for example, U sigma, U delta U transpose, right? Agreed? Do you follow? So now, what is sigma inverse? We know that inverse reverses the order. I will have U inverse transpose. And what is U inverse transpose? Can you tell me? We know that U is an orthogonal matrix according to the properties of SVD or AVD, recall preliminaries. So it's U transpose transpose, so it's U. So I will have this. Also delta inverse and U inverse. And we know U inverse equals U transpose because U is an orthogonal matrix, right? So now let's replace sigma inverse with this term. I will have this. Do you agree that I can bring this U here and this U transpose here? If I bring U inside the parentheses, I know that this transpose is supposed to reverse the order. So I'll have U transpose X and U transpose mu. Do you know why? Apply transpose on this and you will get this again. Because U transpose X becomes X transpose U. U transpose mu also becomes mu transpose U. Let me solve it for you once. So because if I apply this transpose on them, then it becomes X transpose U minus mu transpose U. I can write factor out U, X transpose minus mu transpose U. I can also write it as X minus mu transpose U, exactly what we had here, okay? And also I'm bringing U transpose inside the parentheses, right? What is this? I'm repeating what we found there. Let's simplify this a little bit further. Delta inverse, can I write it as delta to the power of minus half times delta to the power of minus half? Can I write it? I'm allowed to do that. Why? You should be careful to do that. Can I write any matrix? For example, I have matrix A. Can I write it as a to the power of half, a to the power of half? Am I allowed to always do that for any general A? No, because the other way around is true. A to the power of half times a to the power of half is A. But can I write A as a to the power of half times a to the power of half? Not always. I can only do that if the elements of A are non-negative, right? Are non-negative. Then I can decompose it into a to the power of half times a to the power of half. But I'm sure that the elements of delta inverse are non-negative. Can you tell me why? What was this? It was either SVD or eigenvalue. Consider it as eigenvalue decomposition of sigma. So what are the elements of here? Delta is a diagonal matrix, right? And what are the diagonal elements of delta? They are eigenvalues of sigma, right? Sigma is covariance matrix, right? We know that according to the properties of covariance matrix, a covariance matrix is positive semi-definite. When a matrix is positive semi-definite, what does it mean? Its eigenvalues are non-negative, right? So elements of delta, diagonal elements of delta, are non-negative, right? Also, as a result, delta inverse is also non-negative. Why? Because the inverse of a diagonal matrix, according to linear algebra, is the inverse of diagonal elements of that matrix. Right? Right? Okay. So this is, so I'm allowed to write that in this way. Now I'm replacing this with this. Why am I doing that? Because I want to bring this to this parenthesis and this to the right-hand side. I'll decompose that, so I bring the left side to the left side and the right side to the right parenthesis. If I do that, I will have these, because I know that transpose reverses the order. I will have this also. Okay? Agreed? Now, what is this? Can you tell me? Consider a transformation. I'm defining this transformation, which gets x and transforms x as delta to the power of minus half u transpose x, exactly the term that we have here, and here, and here, and here, right? Agreed? As a result, according to this, as a result, basically I don't know if I have written this, it's kind of phi k of x minus phi k of mu k transpose phi k of x minus phi k of mu k. What is this? We just saw. Assume phi k of x is y. What is, and assume phi k of mu k is z. Y minus z transpose y minus z. What is that? Norm, L2 norm, a squared L2 norm, right? Between of the vector connecting y and z, right? That's exactly the squared Euclidean distance between phi k and phi k of x and phi k of mu k. So basically, what is it doing? What is LDA and QDA? What is QDA doing? It says, I have some data points in this space. I call this space input space. I transform my data points to some other space by this transformation. In that space, I use Euclidean distance. I use that simple classifier which the baby could think of. I can't use that simple classifier in the input space because of the distributions of the classes. Let me apply that transformation so the distributions become simple, and then I can use that simple idea of the baby. As a result, it's kind of doing a metric learning. It's learning this transformation. You can see it as metric learning, right? Because in that space, you can use simple Euclidean distance. Please watch these seconds after the watch because that was important. Okay. Watch it after the class. And okay, so yes, metric learning. And let's talk briefly about the metric learning topic in machine learning. I don't know if you have heard of Mahalanobis distance. Have you heard of that? Okay, let me tell you one thing. Consider these two classes. I can draw well. Consider these two classes and a test point here, x. The mean of this class is here, so the distance is this. The mean of this class is here, so the distance is this. What does the Euclidean, simple Euclidean distance tell me? What is the class of x? Circle, right? Now, forget math. I tell you as a human. What is the class of x? You human decide visually. What is the class of x? Star. Star. So of course Euclidean distance made a mistake here. How can we correct this mistake? We can correct that using a distance named Mahalanobis distance. The Mahalanobis distance says, by the way, Mahalanobis was a statistician. And he was at the same time as Ramanujan. I don't know if you have heard of Ramanujan. Ramanujan was a mathematician in number theory. Mahalanobis was a mathematician in statistics. They met in Cambridge. Okay, so Mahalanobis said, let's correct this mistake of Euclidean distance in this way. How, when I ask you as a human, how did you decide that x is in the class of star? How did you decide that? The shape, kind of. So you saw that the star class is bigger, right? So its covariance matrix is bigger, right? As a result, you reduce this distance, the distance of Euclidean distance, by the covariance matrix. The bigger the covariance matrix, the smaller that distance I should assume, right? So what was the Euclidean distance? It was this, right? X minus mu, a squared Euclidean distance. And mu is the mean of the classes, right? But I need to scale it exactly in this interpretation. The bigger the covariance of the class, the smaller that distance should be, right? So let's say x minus mu transpose sigma inverse x minus mu. Sigma is the covariance of that class. This is Mahalanobis distance, right? It corrects, scales the distance. Later, people said, who says that it should be sigma inverse always? Let me replace it with a general matrix A, but there is a but. This A cannot be any matrix. It must have some property. What property? Can you tell me? What was one of the properties of norm, which was very important? I told you once. What? No. Should not be single. No. No, there isn't. So what? There were 4 properties of the norm. Do you remember? And I said that these are also 4 properties of distance metric. What was the 4th one? The donkey one, the triangle inequality, right? Triangle inequality. For this distance to satisfy triangle inequality, A must be positive semi-definite. In other words, for this to be convex, A must be positive semi-definite. Okay? And we know that in Mahalanobis distance, this A was actually positive semi-definite because covariance matrix is positive semi-definite. Sigma inverse also is positive semi-definite. But when we replace it with A must be positive semi-definite, right? Now a big area in machine learning says that let's find this A. So what is my optimization problem? You tell me. Minimize some cost subject to, with respect to what? What is my optimization variable? This matrix A. Now you tell me, what costs can you think of? Assume you are a designer of an algorithm in metric learning. You know that your optimization variable is A. But you need to, your whole paper is talking about one cost. You can think of various costs. What cost can you suggest? What? Mean squared error between what? What? The actual and predicted label, you're saying? I understand what you're saying, but this is a classification problem. Okay, what you're saying is for regression problem. Assume this is a class. So I think your answer is correct, but let me rephrase it. If I have classes, right? Assume my classes are confused with each other in the input space. This metric learning is, as I told you in the previous slide, it's kind of a transformation, right? Let's learn this A in a way that the classes, the distance of the points in the same class decrease and the distance between the classes increase. You are manipulating this distance, right? Manipulate it in a way that the points which are in the same class fall closer to each other, are pushed toward each other, and the points in different classes fall away from each other. Did you understand? By the way, this A also, as I told you, you can see it as a transformation. I told you, I explained this to you, but let me explain it in this way too. X minus mu transpose A, X minus mu. Am I allowed to write it as X minus mu transpose U transpose X minus mu? Am I allowed to do that? I tell you, yes. I wrote A as U transpose. Let me tell you why. Consider eigenvalue decomposition of A. I don't know what notations I use. V delta V transpose, okay? Okay. Am I allowed to write it as V delta half V transpose? Yes, because I assumed A is positive semi-definite. So its eigenvalues are non-negative. So the diagonal elements of delta are all non-negative. Now let me denote V delta to the power of half as U. I define it. So it becomes U transpose, right? Now let's continue where we were. I bring this U to this parenthesis and this U transpose to this parenthesis. What happens? It becomes U transpose X minus U transpose mu transpose U transpose X minus U transpose mu. What is this? Squared Euclidean distance? You tell me. L2 norm, squared L2 norm, or squared Euclidean distance between U transpose X and U transpose Y, mu. What is U transpose X? Please tell me, so I can find out that you have understood everything in this course. Linear projection. U transpose X is linear projection. So basically, this metric learning, the whole thing that I was talking about, is saying that transform data from input space to some other space using linear projection. And then after this linear projection, use simple Euclidean distance. Don't use the simple Euclidean distance in the input space. Did you get it? So transformation can be nonlinear. Here we are having a linear transformation, right?
You mean by we have bigger matrix, then we have small distance? Like how you
So by this example, humans visual system understand that X belongs to the class star.
because the shape?
Because of the shape. Shape is bigger. The scatter, the covariance. Do you agree that the class star is bigger? So its covariance is bigger. Right? Its variance is bigger. This is more spread in the space. Right? Repeat this one. So I'm saying that, what do you agree that Euclidean distance says that X belongs to the class circle, but humans visual system says that it's wrong. X belongs to the class star. Now let's analyze what humans mind doing. It's basically looking at this variance of the classes. It says that the variance of the star class is bigger, so I scale this Euclidean distance to become smaller. The distance of X to the mean of the bigger class should be scaled down. Why? Because of this intuition that, why do you say X is in the class of star? No. Compare these two cases. Compare this. Of course, this Euclidean distance says it is circle, and the same thing, the mean is the same, but its scatter is smaller, and the point is the same place. Human's mind still, in both cases, Euclidean distance says that the point X belongs to class circle, but human's mind in the second case says that Euclidean distance is right, but in the first case says it's wrong. Just because, what is the difference of these two cases? The scatter of the bigger coin, right? Did you understand? Okay.
Learning. So basically, metric, we need to modify the metric here, or we modify Euclidean distance to other metric.
So metric learning means that, consider this metric. A is a positive semi-definite matrix. Let's learn this A. Whatever A you put, it gives you a different metric, right?
Yeah.
So let's learn this to do our goal. This is metric learning. By the way, metric learning algorithms are divided into 3 categories: spectral metric learning, probabilistic metric learning, and deep metric learning. What I just told you is in the categories of spectral and probabilistic metric learning. Deep metric learning is a bit different. It doesn't care about this formulation. Deep metric learning says that I have a neural network. Let me learn this network so it pushes the points, the similar points toward each other and the dissimilar points away from each other. That's called distance metric learning, and the most famous network for that is called Siamese network. Okay, but for spectral metric learning and probabilistic metric learning, this is the idea.
Like
I'm optimizing some cost with respect to A. Do you understand? As I said, machine learning is always optimization, right? So, acknowledgements. For more information on LDA and QDA, refer to our tutorial paper. There are more things on LDA. For example, comparison of LDA and t-test and naive Bayes and these things. I haven't covered those. For more information, see my tutorial paper, linear and quadratic discriminant analysis tutorial. Code of LDA and QDA, you can see it in my GitHub page. Also, for more information on LDA and QDA, you can see Hasty and Tipshirani's book, Elements of Statistical Learning. Some slides of this slide deck are also inspired by teachings of Professor Ali Qudsi and Professor Mujou at the University of Waterloo, and also Professor Hoda Mohamadzadeh at Sharif University of Technology. And these are the references. By the way, we also have the library of LDA and QDA in scikit-learn, right? You can also use that. Let me tell you this quickly, and then we start the break, that scikit-learn of linear discriminant analysis. So we have linear discriminant analysis. Don't confuse it with LDA, because if you see LDA is used as the acronym of 2 things in machine learning. One of them is latent Dirichlet allocation, The other one is linear discriminant analysis. Don't confuse them. You need to use linear discriminant analysis. So as you see, it has usually, so by the way, scikit-learn or scale-learn is also pronounced as scikit-learn, doesn't it? Okay, scale-learn or scikit-learn is usually used for fundamental or statistical machine learning. Okay, so machine learning excluding deep learning, right? So the many of the algorithms that we are talking about in this course, you can find their libraries in scikit-learn. You also have coding question in your assignment, which you use scikit-learn. Okay, so usually the methods in the scikit-learn have fit and fit transform, as you see here. They have fit and fit transform, also transform. So there are three functions: fit, transform, and transform. What do they do? Fit is another name for training. You train, and X is the data, Y is the labels, right? So classifiers, of course, get Y as labels. Regressors get Y as continuous labels, right? And by the way, in scikit-learn, they get data row-wise. Okay, so rows are the number of points and the columns are the number of features. In contrast to what we usually have, which we put the data points column-wise, they put row-wise in code, like what you have in Excel file. Okay, and why are the labels? Fit, so was training. Transform is test, right? Fit transform means train using this X, also test it. So train and test. Okay, and also here we have predict, which says predict the class labels. So some libraries have predict as well. And I think the rest is also you can get the parameters of them. For example, you can use this library and say, I want the estimated mean and covariances of the classes. You can use get params, right? To get these parameters or the priors of the classes. It gives you. So because, for example, sometimes you might be wondering what parameters it used on your data, right? Also predict, you can get the logarithm of log probability of your data. Like I think it will be log posterior because LDA is using posterior, right? And or probability itself. What is a score? It basically means that test your data. It gives you some predicted labels. You also have the actual labels. Compare them. Give me the accuracy, for example. It does that for you, or you can do it separately. You can get the predicted labels, and there are also libraries for calculating the accuracy or the FS score, right? In scikit-learn. So we have the same thing. This was for LDA. We have the same thing for linear regression. We have scikit-learn for linear regression. We also have so it has also fit and fit transform. Fit and fit transform or predict. Predict or transform means test, right? And also we have scikit-learn for ridge regression, for lasso regression, for linear regression, for LDA, for QDA. Again, as I said, LDA, you need to use linear discriminant analysis. Otherwise, it might be latent Dirichlet allocation. And by the way, when you so these are classes, right? These are classes. So for example, linear regression is a class. When you instantiate the class, you make an object of that. You need to initialize its parameters. So it might have some default parameters, or you can set the parameters. For example, if you are using a ridge regression, one of your parameters is what? That lambda, that regularization parameter. It has a default value, but you can change it, right? For example, when you're using LDA, there might be, for example, choices for, I should see which choices it has. For example, choices for estimation of the priors or different things. You can change them, right? They have usually default values, but you can change. So when you are instantiating that class, you can set the parameter. Okay, so let's have a break and come back at 8:45, and then we will continue with SVM. And SVM is one of the coolest algorithms in machine learning, I told you. Okay, thank you.
Why we have work for this?
So PyTorch is a deep learning. PyTorch, so we have several libraries in Python for deep learning. For example, one of them is PyTorch, one of them is TensorFlow, one of them is Keras, one of them was, we had some other things I forgot. Do you remember? What? Scikit-learn, no. Scikit-learn is for machine learning without deep learning. So it's for statistical machine learning usually. By the way, Scikit-learn has neural network, but this neural network is weak. Okay, it's for simple neural network. For deep learning, you need to use PyTorch or TensorFlow. I believe that this is my definition. That, by the way, statistical machine learning means that you use a statistics for machine learning. But in simple words, you can see machine learning excluding deep learning is a statistical machine learning. Excluding. Usually, you can have a combination. So in deep learning, you might also become very theoretical and use statistics. But usually when people say statistical machine learning, it means that fundamental machine learning without a deep learning approach. Usually. So when you use the theories of statistics, whatever you can learn in statistics, you use them in machine learning, in data science. That is a statistical machine learning. You analyze your data by statistics, right? So you're using here, for example, we are using statistical concepts. We are using linear algebra, optimization, also statistical concepts. For example, we sometimes use mutual information. Sometimes you use what? PDE? PDF? Probability. You can see probability as a usually it comes with the statistics, right? A big part of the machine learning is probabilistic machine learning. I believe that you can see it as a subset of statistical machine learning. Someone might say that I'm wrong. This is my definition. And I think, according to my experience, I'm saying that these are statistical machine learning. And also, for example, we'll see that. We will talk about independence, Hilbert-Schmidt independence criteria, which came from statistics. So when we use these statistical concepts in machine learning, we call it statistical machine learning. And they are applied statistics, right? And also in archive, we have machine learning category in two, we have machine learning subcategory in two broad categories. One of them is in CS, computer science. The other one is statistics. According to my experience, whenever your machine learning paper, if you write a machine learning paper, has too much theory, you need to set the primary category as the statistics.machine learning. When it doesn't have too much theory, you put it in CS.machine learning, right? You can use that still statistical machine learning as a second categories, but primary category is depending on how much theory you have in your paper. If your paper doesn't have too much theory, it will be rejected from a statistical machine. Okay. So yes. Okay. So now we talk about support vector machines, which is very cool. One of the coolest algorithms in machine learning, especially if you like math, because I think this is one of the most theoretically sound algorithms in machine learning. Yes, but I updated one of the slides and I will update that. I haven't yet updated that. But one of the slides, only one is changed. Okay. So SVM first, let's talk about SVM versus perceptron. Perceptron was proposed by Rosenblatt, which was a physiologist, in 1958 at Cornell Aeronautical Laboratory, and it was a neural network for binary classification. So in Cornell, Rosenblatt proposed just try to model a neuron, a biological neuron. Okay. By the way, I don't go into the depth, much depth of the perceptron. I have talked about it more in my deep learning course. Okay. But here for comparison, I need to briefly talk about it. In later attempts, Hebbian learning, proposed in 1949, was used for learning in perceptron. Okay. So Hebbian learning was saying that when two neurons are fired together often, then the relation between these two neurons gets stronger and stronger. So this is what Hebb found, and Hebbian learning tries to mimic that idea for training a neuron. Okay, this was perceptron. So perceptron, however, cannot generalize well enough, because for linearly separable classes, it finds one of many possible decision boundaries. Do you agree that, consider these two classes, they are linearly separable, right? But so you can have linear decision boundary between them, but you have too many choices, right? Whenever you start training perceptron, because perceptron is trained iteratively, right? So, and we know that iterative optimization depends on its initial solution. So you need to initialize the weights in perceptron. Whatever initialization you start with, you will end up with one of the linear decision boundaries. All of them are correctly classifying the training set. However, they are not all of them are good for classifying a test point. For example, consider this decision boundary. It's not good in generalization. It doesn't generalize to test data. Why? Because consider this test point. This test point is in the circle class. However, as this decision boundary is very close to the circle class, it estimates the class of this test point as a cross point, right? So it's an error, so it didn't generalize well. As a result, sometimes perceptron might give you a good answer. For example, this one is a very good answer, right? However, not always. So someone named Vapnik, who was a great mathematician, he's still alive. Lex Friedman has an interview with him, and he's originally from Russia, and you know that Russians have a very good talent in mathematics, right? Vladimir Vapnik et al. Proposed linear SVM in 1974. They were motivated by the fact that by this flaw of perceptron. Okay, they said, okay, perceptron cannot generalize well. Let's find the best decision boundary among them. Which one is the best decision boundary among them? Of course, this one, right? Let's design an algorithm which doesn't converge to one of the possible decision boundaries. Let's find the best one, right? For better generalization. So they proposed linear SVM. Linear SVM's idea, if we want to say with an example of with a story, assume I have two teams of children. Okay, I have two teams of children, and so assume these are the teams of children, right? And so there is a wall between them. There is some wall between these two teams of children, and they want to say which team is stronger. So of course they will push the wall toward the other team. Okay. Of course, the person who is closer to the wall in the team has a more impact, right? The person who is at the back of the team is doing nothing, right? So this person who is next to the wall is important. Also, this person who is next to the wall. And these people are pushing the wall toward the other team. So now these two teams or these two people are equally strong or equally weak. Then what happens? The wall stands exactly between them, between the two teams, right? And this distance, these two distances will be equal to each other, right? This is the exactly what we find by SVM. The SVM decision boundary stands exactly between the two classes. So the two teams can be seen as the two classes, and the wall can be seen as a linear decision boundary, right? Here is a plane, and the people who are next to the wall from the two teams are called support vectors. Okay, called support vector. Hence the name support vector machine. And why is it best for the wall to stand exactly between the two classes? Because this is the best for generalization, right? If a test point is here, it's supposed to be in the circle class. And if the test point is here, it's supposed to be in the cross class, right? As a result, so SVM tries to find the best decision boundary rather than one of the possible ones. The best decision boundary is the one which has the largest distance from the closest points of the classes to the decision boundary, right? This is because those points are also closest points to the other classes to each other. So because these 2 points, why are these very important? Because they are most capable of being confused with the other class. They're closest to the other class, right? Therefore, they are most capable of being confused. These points are called support vectors. Okay, now let's go talk about hard margin SVM. So the initial SVM which was proposed was hard margin SVM. So in this lecture slide, we'll talk about hard margin SVM, soft margin SVM, and kernel SVM. We go to them one by one. So hard margin SVM. Now, so far it was introduction. Now let's go into the mathematics. We want to find a linear decision boundary, right? A linear decision boundary, because SVM is linear classifier, where one class falls in one side and the other class falls on the other side. Agreed? Okay. The equation of a line, which for the linear decision boundary is this, right? Beta transpose x plus beta 0 is 0, equals 0. This is an equation of a line, a fine function, right? Where x is a d-dimensional data point. Agree? Of course, if x is on the line, it satisfies this equation, right? Beta is also d-dimensional vector, and that's a normal vector of the linear line. What do I mean? Consider this line. This beta is a normal vector, which is perpendicular to the line, right? Beta 0 is the bias or intercept of the line. Agreed? Now, consider any 2 points, x1 and x2 on the decision boundary, like this, right? Any 2 points. So as they are under this linear equation, on the linear decision boundary, they must satisfy equation 1. Agreed? So I have this and also this. Beta transpose x1 plus beta 0 is 0. Beta transpose x2 plus beta 0 is 0. Right? They must satisfy the equation of the line. As a result, they are equal to each other. Right? So these two beta zeros can be cancelled and bring one of them to the other side and factor out beta transpose. You will get this, right? What does this mean? This is a vector. This is also a vector. Some vector transpose another vector means that the inner product between these two vectors, if it is 0, what does it mean? When the inner product between two vectors is 0, what does it mean? Those two vectors are perpendicular, orthogonal to each other, right? So beta is orthogonal or perpendicular on the vector x1 minus x2. And what is x1 minus x2? Is a vector connecting x2 to x1, right? So the vector connecting x2 to x1 is this, and this is beta. We just proved that beta is a normal vector, which is orthogonal to the line, right? Because x1 minus x2 is on the line. Now consider a point x0 on the decision boundary, right? Some x0. And the point x on one of the sides of the decision boundary. So the x0 is on the line, and x is on one of the sides of the decision boundary. Therefore, as x0 is on the line, it must satisfy the equation of the line. So beta transpose x0 plus beta 0 must be 0. Rearrange the terms. This is beta 0. So beta 0 equals minus beta transpose x0, right? Now, what is the distance of this point from this line? What is the distance of this point from this line? It's this. This is the distance, right? So this distance is also this distance. What is this distance? How can I calculate it in geometry? We learned that. This distance is exactly the inner product of this vector and this vector, but one of them must be normalized, right? To recall your geometry classes. So when you have two vectors, what is this distance? You calculate the inner product of this and this, but this must be normalized, right? So basically beta transpose over the L2 norm of beta, because I'm normalizing beta. And why do I have transpose? This is exactly inner product between beta and x minus x0. This vector is x minus x0, the vector connecting x0 to x, right? So basically the distance of the point from this line, I denote it by d, is this, right? Clear? Okay. Now I bring this in the numerator. So I'll have this beta transpose x minus x0 over length of L2 normal of beta. So I apply this in the parentheses. I will have beta transpose x minus beta transpose x0 over L2 normal of beta. Now I use equation 2. Replace minus beta transpose x0 by beta 0. Right? So I'll get this. So far clear? We know that a distance is a non-negative value, right? Can a distance be negative? No. Distance is non-negative, 0 or positive, right? Therefore, I need to use absolute value on this, because this might be negative, right? Actually, if you put x on this side and beta is in this side, this equation 3 becomes negative. So I need to have absolute value. So but we know that denominator L2 norm is non-negative, so I can bring it out of the absolute value. So I will have this. However, absolute value is a pain in the neck in mathematics. Why? Because we know absolute value is not as smooth at origin. Whenever we see absolute value, we always are sad. Okay. We want to get around of it somehow. Okay. Especially in optimization, right? Because it's non-smooth. And you need non-smooth optimization to solve that. So but we can use a trick in machine learning. In machine learning, this trick is used a lot. Here, I'm assuming that because it's binary classification, I have two classes, right? So I can name the labels anything I want, right? I let the labels be +1 and -1. Why don't I use 0 and 1? Because of the reason that I'm gonna explain. Because of this technique, I'm assuming that the labels are either 1 or -1 for each of the classes, right? So if y is +1, assume the points which are above the line are their labels is 1. For the points which are below the line, their label is -1, right? So if y is +1, beta transpose x plus beta 0 is greater than 0, because we know that beta transpose x plus beta 0 equals 0 is the equation of the line. Greater than 0 is above the line. Less than 0 is below the line. When y is +1, it's greater than 1. When y is -1, it's less than 1. Do you agree that if I multiply y and this is always non-negative? I just showed you in equation 4, right? It's always non-negative, because 1 times a positive number is positive, -1 and negative times a negative number is also positive, right? So in the numerator, rather than absolute value of beta transpose x plus beta 0, I use y times beta transpose x plus beta 0, and I don't need absolute value anymore. Did you see the technique? It is a delight technique used a lot in machine learning. And now you understand why in machine learning, sometimes they use -1 and 1 for binary classification. Sometimes, why do they use labels +1 and -1? Usually because of this, okay? So this is a distance, right? Without absolute value. This distance from decision boundary, this is the distance from the linear decision boundary, is either 0 or greater than 0, right? Because it's always non-negative. When x is on the decision boundary, the distance is 0. When x is not on the decision boundary on either side, it's greater than 0, right? Okay. Now suppose there are n data points, not just one data. We have data set, n data points, and their class labels are y1 to yn, right? And we know that labels are +1 or -1. So yi is either 1 or -1 for all I from 1 to n. The closest points to the decision boundary are more at risk of being confused and misclassified, right? Because they're closest to the other class. In each of the data, the closest points to the decision boundary are called support vectors, as we talked about, right? Okay. Now we want to do what? We want to maximize the margin or gap between the support vectors and the decision boundary. Of course, whenever I have said it several times, whenever you want to understand an algorithm, put yourself in the shoes of the designer of the algorithm. Now assume you are Vapnik. Okay? How can I make generalization the best? For each of the classes, I want to be farther from the decision boundary, right? But I have two. If I had only one class, the decision boundary would be infinite, right? Go to infinite. However, I have two classes, each of which wants to push the decision boundary away. So I need to stabilize between them. So of course, for the support vectors from the two classes, I need to maximize the distance, their distances from the decision boundary, right? So the decision boundary becomes as far as possible from data for having least amount of misclassification, right? So as I said, everything is optimization. Maximize this distance, right? But with respect to what are the optimization variables? Beta and beta 0. What are the parameters of this line? Decision boundary. Beta and beta 0, right? So with respect to beta and beta 0, maximize this distance and di, right? Here, for now, assume I goes from 1 to n. Assume that I'm calculating the distance, I'm maximizing the distance of all of the points from the decision boundary. At the end, we will see that all of the other ones will be ignored. Although we started from maximization of distances of all points from the decision boundary, we will see that only the ones will be in effect which are closest to the decision boundary. We will see that, okay? Maximize this di, and this was the di that we talked about. for all I from 1 to n, right? This can be converted to a minimization problem. So there are several techniques for converting maximization to minimization. Either you multiply the cost function by -1, or you use the reciprocal of the cost function, right? Here, I'm going to use the reciprocal. Minimize the reciprocal, right? So now, I'm repeating what we had. Assume now we desire to find a decision boundary which has some distance from data of classes. So the distance of points are positive for support vectors. So let me recall. Yeah, assume that your decision boundary has some distance from the closest point to it, right? So assume, let the constant s denote the smallest distance to the decision boundary. So let s to be the distance of the closest point to the decision boundary from the decision boundary. Did you understand? Which is the distance of the support vectors from the decision boundary. Then, do you agree that all of the distances are greater than or equal to s? Because s was the smallest distance, right? Okay. As this expression is greater than or equal to the constant s, we can assume that its numerator is greater than or equal to some constant c, right? Because s times assume that s times the denominator, I consider it as c, okay? So I'm assuming that the numerator is greater than or equal to some constant c, and this constant c will be one of the hyperparameters of the SVM. Okay, so this equation appears in the denominator of equation 8 here, right? Agree? We can convert the optimization problem 8, which was this, to minimization of its numerator while the denominator satisfies equation 9. So basically, I'm saying that rather than minimizing the fraction, minimize the numerator, but use this constraint equation, this restriction of equation 9 as the constraint of the optimization problem. This is also used a lot in machine learning. We saw an example of this, a similar example of this in optimization of Rayleigh-Ritz quotient. Recall preliminaries. In Rayleigh-Ritz quotient, we also optimize the numerator subject to the denominator, some constant on the denominator. So this technique is also used a lot in machine learning. So it is simpler. So here we are minimizing the L2 norm of beta, right? It is simpler to minimize a squared L2 norm of beta times half, times 1/2. Why? First off, because a squared L2 norm is quadratic and convex, right? But L2 norm is not convex. Okay? I want my optimization problem to be convex optimization, which is easier. Okay. Why do I use 1/2? Because exactly, because derivative of a squared L2 norm of beta becomes 2 beta, and I want that 2 to be dropped, right? So the optimization problem is this now. The constant c here can be any constant, which is not important because not having effect in derivative, because derivative of a constant is 0. Because, for example, when we have Lagrangian, then we take derivative of Lagrangian, right? Then it goes away. We saw a similar thing when we were optimizing, again, the Rayleigh-Ritz quotient in preliminaries, right? You said the constant, that constant is not important. Yeah.
The same optimal solutions.
So the question is whether the solution of equation 10 and 11 are equal. I believe they are not equal, but I'm forming the optimization problem. I'm telling you the line of thought of Vapnik. But I think they're close to each other. The solution of equation 11 is close to the solution of equation 10. And it is close enough, I believe. But as far as I know, I might be wrong, but as far as I know, optimization of L2 norm is not equivalent to optimization of a squared L2 norm. But we usually use a squared L2 norm, so it is convex. But why do I say its solution behaves similarly? Behaves because the bigger the beta, the bigger the L2 norm, the bigger the squared L2 norm. That's the reason. The behavior is almost the same. Usually, we use c equals 1 as a constant because the simplest scalar constant. So here, this one, I can convert it to a less than or equal to inequality, right? Because it's easier. Usually, in general form of optimization, we usually, if you pass any optimization course, they usually have less than or equal to. We can do that, okay? What is the Lagrangian of this function? Recall preliminaries. We talked about this. So Lagrangian is the cost, right? Plus, so we have n constraints. This is not just one constant. We have n constraints, right? And therefore we have sum over n constraints. And this is the constraint times some dual variable, or also called Lagrange multiplier, right? Alpha I. Agreed? Alpha i's, alpha 1 to alpha n are the Lagrange multipliers, right? So this is Lagrangian, and it's a function of optimization variables and the Lagrange multipliers, right? Now, this is the Lagrangian. What should we do? We want to minimize it. Minimize Lagrangian, which is an unconstrained optimization problem. What did we do in high school? Take derivative, set it to 0, right? First order optimality condition. Take derivative with respect to each of these variables. With respect to beta, you tell me what is the derivative of this first term with respect to beta? Derivative of a squared L2 norm of beta is 2 beta. 2 cancels with 1 over 2, so we'll have beta. This summation inside of this, it has, you multiply these, alpha I times c is constant with respect to beta, goes away. So I only have this. Alpha I times yi times minus, so minus comes behind the summation. This is alpha I, this is yi. What is the derivative of beta transpose xi with respect to beta? Xi. Why do I have summation? Because here I'm taking derivative with respect to beta. Summation is over I, right? If I were taking derivative with respect to xi, the summation would go away because it would be derivative with respect to a specific I, xi, for a specific I. Here, I'm taking derivative with respect to beta. Summation still remains, right? Agree? Set it to 0, 0 vector, because beta is a vector. Rearrange the terms, beta is this. This is one of the formulas of SVM. We just derived that. Okay. So we found beta with respect to alpha I, yi, and xi. Now take derivative of Lagrangian with respect to beta 0. So what should we do? So the first term goes away. It's constant with respect to beta 0. We know that alpha I times c is constant with respect to beta 0. So we only have minus here, and alpha I times also yi, what? Times beta 0. Its derivative is 1, right? Right? So go. Still we have summation because it's taking derivative with respect to beta 0. Summation is over I. Set it to 0, but this 0 is a scalar 0. because beta 0 is a scalar, right? Right? Therefore, this is equal to 0, right? Now, this was the Lagrangian, right? Let's substitute what we just found, equations 12 and 13, the beta and beta, this equation, in the Lagrangian. So what happens? By the way, here, what I'm doing is called the method of Lagrange multipliers. The steps that I'm doing is called the method of Lagrange multipliers. For more information, see my optimization techniques course in my YouTube channel. Okay, I have explained that. So, but I think you understand what I'm doing, right? I'm taking derivative of Lagrangian with respect to optimization variables. I'm just now I put what I found in the Lagrangian. What happens to the first term? Let's see. So the first term, we know that squared L2 norm of beta transpose beta is quadratic, right? What was beta that we just found in equation 12? This one, right? So I'm using this transpose this. This transpose this. We know that this is a scalar, this is a scalar. Transpose does nothing on them. But this is vector. So because xi transpose. Right? Therefore, I have xj transpose. By the way, here for one of them, I'm using j index, the other one for I index, not to confuse the indices, right? Did you understand? Now I can bring this summation here, right? So I'll have these two summations, double summations, and also have alpha I, alpha j, yi, yj, xi, transpose xj. This was xj transpose xi, equivalent to xi transpose xj. Right? Now the second term. So this was the second term. Let's multiply the terms to each other. So I have this times this times this, also this times this. So it gives me these three terms, right? Do you follow? Okay. Now, can I bring this beta transpose out of the summation? Yes, because it doesn't depend on I. So I'll have beta transpose this and the rest of the terms. What about beta 0? I can bring it out. What about C? I can bring it out. They don't depend on I, right? Did you understand? Okay, so now what do we do? Now I replace beta with equation 12. So I have beta transpose, therefore I use xj transpose. And I'm using index j not to confuse with index I here. And this is repeated here. And this minus is also here, right? What about this term? We just saw in equation 13 that this term is 0. Right? So this goes away. Interesting. And the last term is here. Now I bring this summation back, so I have double summation. And also this, and this is the last term. So far clear? I just simplified the terms. I substituted those two equations in my Lagrange. So the Lagrange, when I substituted these things, these beta dagger or beta cross means that what I found for beta and for the equations 12 and 13. Okay, so when I substitute these, this is exactly what I found. I just showed you how I derived this, right? So when you substitute, so when you take derivative of Lagrangian with respect to your primal optimization variables, which were beta and beta 0 here. By the way, we have two types of optimization variables: primal variables and dual variables. Why? Primal variables are the variables which were our optimization problem was optimizing over. For example, What were the optimization variables? Beta and beta 0. These are called primal optimization variables. What are dual optimization variables? The Lagrange multipliers, right? So you have the Lagrangian, which is a function of primal and dual optimization variables, right? When you take derivative with respect to primal optimization variables set to 0, find some things and substitute them back in the Lagrangian becomes only a function of dual variables, right? When you do that, when the Lagrangian function becomes a function of dual variables, we call that dual function. And it's usually denoted by G. The primal cost function, they usually are denoted by F. The dual variable, they usually denoted by G. It's just naming, not important, okay? So G is only a function of dual variables, alpha I, alpha 1 to alpha n, right? And as you see, it's only a function of alphas, right? There is no beta in them, beta and beta 0. Interestingly, this is this term. Half of something minus that thing is minus half of that thing, right? Equation 14 is my dual function. Okay. Now, let me tell you one thing. Whenever in my optimization problem, when I'm minimizing my primal function, I should maximize my dual function. It's the other way around. Why? Because for you to imagine that you have a bowl, which you want to minimize that bowl. Dual function is an upside down bowl, but you want to maximize it. And there is a gap between these two. This gap might be 0 or non-negative. This gap never gets negative. It can be proved. See my optimization techniques course for more information. It can be proved that the distance is always, this gap is either 0 or positive. If it is 0, it's a strong duality. I think it was, yeah. If it is a positive gap, it's weak duality. Okay, these are terminologies in optimization. Don't worry about it. Okay. So did you understand? So this is a bowl. This is the other way. There is a gap between them. Okay. This is F. This is G. Okay. So sometimes minimization of the primal function is hard. We convert it to maximization of a dual function. Sometimes dual function is easier to optimize. No, that's not the case. Sometimes the formulation of dual function becomes easier. Sometimes it's easier because they are different functions, right? That G is a function of Lagrange multipliers, but if F is a function of primal variables, right? So when you are optimizing F, you are optimizing with respect to primal variables. When you are optimizing G, you are optimizing with respect to dual variables, right? And by the way, although their x-axis is different, so x-axis for F is the primal variables, x-axis for G is the dual variables, but their solutions are corresponding to each other. And what do I mean? Argmin of F corresponds to argmax of G. Did you understand? They correspond to each other. So also, according to the dual feasibility in Kay-Roche-Kohn-Tucker conditions, don't worry, I know its name might be scary, but optional. If you want more information, go and see the KKT lecture in my optimization techniques course. Optional. But when you go and watch that, you will see it's very easy. Very easy. It suffices for you to know calculus. And if you follow my steps there, you will understand KKT. Okay. So in Kay-Roche-Kohn-Tucker or KKT, we have, according to the dual feasibility, all of the dual variables for inequality constraints, which are less than or equal to, must be non-negative. So because we can have dual variables for equality constraints and inequality constraints, right? Here we don't have any equality constraints. We only have inequality constraints, right? Agree? And if my inequality constraint is less than or equal to, and my optimization problem is minimization, it can be proved that the dual variables corresponding to those inequality constraints must be non-negative. For proof, see my optimization techniques course. Okay. That is the reason I converted my constraint to less than or equal to. Right? So all of the alpha i's must be greater than or equal to 0. Let's put them all together. So I'm maximizing my dual function with respect to my dual variables. I just talked about this one. My dual variables must be greater than or equal to 0. Where did this come from? This is exactly equation. You tell me. 13. Right? Because that can be considered as a constraint on alpha, right? Let's put all of this together. It becomes an optimization problem. This optimization problem is called dual optimization problem. So do you remember I told you we minimize f or maximize g? Minimization of primal function f is called primal optimization problem. Maximization of dual function g is called dual optimization problem. Okay? So this is my dual optimization problem. Now we define alpha. So we put, now I want to write equation 16 in matrix form or vector form, right? These are element wise, right? So let's put all of the alphas as next to each other as a vector alpha, which is n-dimensional, right? Why n-dimensional? How many constraints did I have? N constraints, right? Because I had n points. Each point has had some distance from the decision boundary. So I have n dual variables, right? Because I had n constraints. Also, I have n labels. I put them next to each other, vector y. Also, I define the vector 1. And the matrix S, whose ijth element is this. So I want this to write this in matrix form. And I know that here, what do I have? You tell me. Yi xi transpose, yj xj, right? I define a matrix S whose ijth row and jth column is this. Now I can write these in matrix form. Let's see. Here I have alpha I, alpha j, so I can write alpha transpose alpha. In the middle of them, these are the elements of S. I have minus half here, right? What about here? I have C. Also, I have summation of alpha I. This is a good technique in machine learning. When you have summation of elements of a vector, you can write it as 1 transpose that vector, or that vector transpose 1, right? I mean the vector of 1 transposes that. So this is exactly what I did. What about this one? What is this? Alpha I, yi, summation. It's just the inner product between the vector alpha and the vector y. This must be, sorry, this is scalar 0, sorry. Scalar 0. What about this? When I say alpha I is greater than 0, it means that all of the elements of the vector alpha must be non-negative, right? We denote it in this way. We denote inequality for vectors a fancy like this. This is called generalized inequality, okay? For vectors, it means that you apply this inequality for all elements. For matrix, again, you can define the cone. The default cone is positive semi-definite cone. Basically, when you say A, matrix A is this, what does it mean? It's positive semi-definite. Because the default cone is positive semi-definite cone. You can determine the cone here with respect to which cone, right? But when it is vector, it's simple. It means that element-wise. Okay. So now what is this? This or this, doesn't matter. What is the cost? The cost is quadratic with respect to alpha, right? My optimization problem is variable is alpha, vector alpha. It's a quadratic function with respect to alpha. These are also linear constraints with respect to alpha, right? When the cost is quadratic and the constraint is linear, affine, this is called quadratic programming in optimization problem. We have a standard convex optimization problems. First off, it's convex. It's convex optimization problem, right? Everything here is convex. Constraints are convex. Cost is convex. Also, its cost is quadratic form. So it's a quadratic programming problem. Whenever in optimization, whenever you can formulate your problem as a convex optimization, you can be happy because you can definitely solve it easily, right? And that's why Vapnik got very happy when he could formulate his problem as a quadratic programming problem, right? And it is a concave optimization problem because we're maximizing, not convex, sorry, because convex, we minimize that. It's a concave optimization problem. So it has one global solution, right? Now, do you understand? Now, do you get it why SVM only finds the best solution? It finds only one solution, not multiple solutions, only one solution. That's the global best, global, right? It's concave. It has only one solution. If it wasn't concave, we had to solve it iteratively. And every time we would probably converge to one of the local solutions, right? Because when it is not concave, it might be like this, right? Depending on the initial solution, we might converge to this solution or to this solution. But when it is concave, no matter where we start from, we will end up to the same solution. Because for solving quadratic programming, we still do it iteratively in optimization toolboxes. But we don't care about initialization because we know that we'll have only end up with the same solution. Now, let's talk about KKT conditions. Now let's analyze SVM, right? Yeah, yes. We can solve SVM either by primal optimization problem or dual optimization problem. Usually we use dual optimization problem. I think, as far as I remember, it has a strong duality. The gap is 0 here. Yes, there is a condition named Slater's condition. Slater's condition. For more information, see my optimization techniques course. Slater's condition, if it is satisfied, we have a strong duality. Okay. Now let's, by the way, I will talk about its test phase, training phase. This was training phase, right? I will tell you how we use these. Before that, let's analyze it. Let's analyze KKT conditions. So Kairos Kontaker or KKT conditions are 4 conditions. By the way, why do we call them KKT? Let me tell you a history. It was called Kairos. No, it was called, there were 2 people named Kohn and Tucker in Europe. Okay. They proved these conditions. They published it. And it was a breakthrough in optimization. So they called it, people called it Kohn-Tucker conditions, right? At that time, I think it was a century ago, I'm not sure when exactly. At that time, it was a competition, scientific competition between Europe and US. So people in US went and said, probably we had found it sooner. They went to the libraries, and someone suddenly found a master's thesis on optimization. In the middle of that, apparently that person whose name was Kairos had proved it. Okay, but it wasn't published as a paper. as it was a master's thesis, no one had read it. Okay, so they said, oh, we found it sooner, US won. But they didn't accept that. After a while, they decided to name these conditions K-Roche contact. And in short, is KKT. Okay? So this is the history. So these are the conditions. A stationary condition says that the derivative of Lagrangian with respect to primal and dual variables should vanish to zero. Exactly the first order optimality condition that we learned in high school, right? Because we are minimizing the Lagrangian. We already used this, right? Primal feasibility says that the constraints should be satisfied in the primal optimization problem. Of course, it's obvious, right? The constraints should be satisfied. We had n constraints. Dual feasibility says that in minimization problem, for less than or equal to inequality constraints, the dual variables should be non-negative. And it has some proof. You can see my optimization course, right? We already used that too. There is another thing which is complementary slackness. What is that? It says that the dual variable alpha I times the inequality, if you bring all of the inequality to one side, right, is equal to 0. What does it mean? When alpha I is 0, when alpha I is not 0, this constraint must be 0. When the constraint is not 0, this is not 0, this alpha I must be 0. Did you get it? They can be both 0 too. But when one of them is not 0, the other one must be 0 because of this equal to 0. Did you get it? Now we are going to use that to talk about support vectors. Do you remember? I said starting the optimization, I said we are considering the distances of all points. Now using this complementary slackness, we'll see that all other points are not important. Only support vectors will be important. What?
Any operational meaning of this?
So exactly the analysis that I said. So what was that? The constraint was this, right? Minus yi beta transpose xi plus beta 0 plus z is less than or equal to 0. This was the constraint, one of the constraints, right? And its dual variable was alpha I. Its corresponding dual variable was alpha I. What does this say? It says that whenever this is not 0, so because this is less than or equal to 0, it's either 0 or less than 0. Whenever it's less than 0, it's strictly less than 0. Right? This alpha I must be 0. Whenever alpha I is not 0, this must be 0. Whenever one of them is not 0, the other one must be 0. They might be both 0 too, right? Did you understand? No, it's not. It's pure optimization. It has proof. See my optimization techniques course for that. I'm going to use this to analyze SVM. Okay. So this is what we said, complementary slackness. Now, according to equation 19, which was the constraint in the primal optimization problem, this is a constraint, right? And also this condition that we had, the dual variables are non-negative, right? So two cases happen. According to this, do you agree that we have either alpha I is 0 or greater than or equal to 0? Do you agree? Right? And also according to this quantity is either greater than C or equal to C. Do you agree that? Because of this. If it is greater than C, what happens? This is not 0, right? Therefore, alpha I must be 0 according to this equation. If this is equal to C, this part is 0, right? And this alpha I might be greater than 0 or might be 0. Did you get it? Is everything clear? Here, again, alpha I might be 0 or might not be 0. But for this first case, it must be 0. I'm repeating what we had here. Now let's see how it interprets in SVM. What does this mean? Can you tell me? What was C? The smallest distance, right? Do you remember? It was the smallest distance was S, but the numerator was equal to C for the smallest distance, right? When this happens, it means that the point xi is on the margin. So, by the way, consider this decision boundary. The support vectors are on some margin, imaginary margin, right? No point is beyond this margin. Do you see that? These are the closest points to the decision boundary. They are on margins. These are called support vectors. And according to just this equation, their dual variables might be 0, might not be 0. Might be 0 or greater than 0. Agree? What does this mean? This means that they are the points outside of the margin. Their distance is greater than C. Right? So these points, for example. For them, alpha I is 0. Their dual variables is 0. Right? In summary, in hard margin SVM that we are talking right now, support vector is defined as the points on the margin boundary, right? Margin around the decision boundary. According to equation 20, what was that? According to this, alpha i's are greater than or equal to 0. The range of alpha I corresponding to the point xi, alpha is greater than or equal to 0, right? Now, then various cases might happen in this range. If the point xi is a non-support vector outside of the margin, right? Which is outside of the margin, then alpha I must be 0. We just saw that, right? If point xi is a support vector that is on the margin boundary, then alpha I is greater than or equal to 0. Now, according to equation 16, right? What was the cost function in the dual optimization problem? It was this, right? Do you remember? Do you remember the dual optimization problem? This was its cost. For non-support vectors, we just saw that alpha I is 0. Put alpha I equals 0 in the cost function of the dual optimization problem. What happens? The cost becomes 0. Put alpha I equals 0 here. We have alpha I, also alpha I here. Put them 0. 0 plus 0 becomes 0. Right? So basically, you're maximizing 0. You're maximizing a constant. Nothing happens. Their impact goes away in the you tell me, in the optimization problem. And as you see, we have summation. So we have a summation of terms. Some of these terms will be 0. The cost will only have the terms for support vectors. Did you understand? Did you understand? Interestingly, we started from the distances of all points, but finally we saw that only the points on the margin, only the support vectors are in effect. As a result, SVM is a sparse algorithm. It only considers some few points next to the decision boundary. Intuitively, it also makes sense because those are not that much important, right? And this sparsity is good. Why? Because of betting on the sparsity principle, which we talked about, and also Occam's razor. right? We talked about these. Very interesting. Very interesting. Now, what is it saying actually? What is this sparsity saying? What is this analysis saying? That consider these. These are the support vectors. Move one of the non-support vectors. As long as this non-support vector doesn't pass the margin or doesn't come to the margin, if it passes the margin, it itself becomes one of the support vectors, right? As long as you are here, right, you move it however you want. It doesn't change the decision boundary. The decision boundary doesn't care. But move one of the support vectors. The decision boundary moves. Did you understand? Now the test phase, and I will finish. So optimization problem 17, which was the dual optimization problem, right? We'll solve that using optimization toolboxes. We can solve it in various ways. For example, one of the techniques to use to solve that is interior point method. We talked about it in the preliminaries, right? You can solve it using interior point method. Or there are also specific algorithms for solving quadratic programming. So using any technique that you want, usually they are iterative techniques. We solve them, but we are not worried about being iterative. Why? Because it's a concave optimization problem. It has only one solution, no matter what we choose for initialization. Using any optimization toolbox, we solve them, such as interior point algorithm. Therefore, we find alpha, the vector alpha, which are the dual variables. Of course, this vector alpha will be sparse, right? A lot of zeros in it. Only support vectors might be 0 or might not be 0, right? So it's a sparse. The optimum alpha, now we put it in equation 12. Do you remember this? We found it. We found this equation. Now we put this alpha, the elements of alpha in this equation, right? Xi is known, the point, right? The point. This is the training data point. Xi is the ith training data point. Yi is the ith label, right? Alpha I, we just found it by optimization. So beta is obtained. Beta was one of the primal optimization variables. We just found it indirectly. Also, as discussed in KKT conditions, for any support vector xi, which is on the smallest margin to the decision boundary, right? We have this. Do you remember? Do you remember? We had this equation. It equals C because it's on the margin. Then putting the obtained beta here in this equation gives me beta 0. Do you agree? Because yi, what is ii? Is the label of the ith point, but I'm assuming that xi is a support vector, right? So yi is the label of the support vector point. Is known. Beta, we just found it here. Xi is the support vector. C is known. For example, a constant 1. Do you remember? But by the way, C, we use C in the dual optimization problem. So C had its impact in the dual optimization problem. So beta 0 is found, right? However, a philosophical question occurs here. We might have several support vectors. Which one do we put in this equation? Whatever support vector you put, you get another beta 0, another value for beta 0. Do it for all of the support vectors and take the average between the beta 0s. That will give you the beta 0, right? Because you have support vectors from both classes, use all of them. Then, so here it gave you beta, this gave you beta 0. Now I can use that. I can take the sign of beta transpose x plus beta 0. It gives me y hat. Why? Do you remember? At the start of the algorithm, what did you say? Whether we are above the line or below the line. This is exactly the sign. Above the line is positive, below the line is negative. The labels, the training labels were +1 and -1, right? By the way, here x can be either a training data point or test data point. It's right? For finding beta and beta 0, we use training data points. But here, this X might be a test data point or training data. Did you understand the test phase? This was hard margin SVM. In the next session, we'll continue with soft margin SVM and kernel SVM. Okay, and the next algorithms. By the way, feel free to do the assignments, and there are some questions which need the next session too. Okay, thank you.